I know what's going on-ish. Welcome, welcome. Chapter 8, Speed Dating. I'll be your host, Dr. Brian Wilcox, for this event. So 10 minutes or so. We'll probably do 2 parts. So this chapter really breaks into what are enzymes, what factors influence enzymes, how do they work, and then it goes on to kind of elucidate 2 of the most famous metabolic enzymatic sets of reactions, photosynthesis, cellular respiration. You do not need to know these extremely complicated series of biochemical pathways in extreme detail. Please pay attention to how I cover photosynthesis and cellular respiration. That's the level of detail you need to pick up. It's a 100 level class. We're sure as heck not going to get into all the finer points of glycolysis and phosphoglyceraldehyde turns into blah, 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 blah. No. So we're going to understand the key concepts of how energy is generated and transformed and whatnot. So that's kind of what we talked about there, what we'll focus on. All right, so a little bit about equations and chemical transformations in general. Again, the arrow represents the change in matter and energy, the chemical transformation, the chemical reaction. Anything after the reaction is produced by the reaction. These are products. Anything before that's reacted upon are reactants. Except in metabolism, the chemical reactions inside of life in cells, most of those involve little protein catalysts that help do the work. These are called enzymes. We write the name of the enzymes above the transformation to show that they're not changed. They're important. They're essential to the reaction, but they're not reacted upon, nor are they produced by. So we give a special name. These are still products. But what do we call reactants in enzymatic reactions? Substrates. Substrates, excellent. So for the biochemical tests in the lab, almost all the biochemical tests are named after the substrate. Starch agar, you're seeing if the enzymes break down starch. Blood agar, you're seeing if the enzymes break down blood. Triple sugar iron, you're seeing if they use the sugars or the iron. The citrate, you see if there's only one test that is named after the product of the reaction. That was the indole test. What was the substrate for the indole test? It was tryptophan, the enzyme you test for, tryptophan ACE. But that's generally the pattern. So you must understand what substrates are. So we can describe reactions as either requiring energy to make them happen or releasing energy. So the way we understand matter and energy, everything since the Big Bang just wants to fall apart and get more chaotic and more disorganized. The universe is heading towards entropy. Entropy is either chaos and disorder, but it's also stability. That's kind of a weird pairing. Chaos and stability seem like antonyms of one another, not synonyms. But chaos is stable in the fact that it will stay that way. This building wants to turn to dust and become chaotic and unorganized. And once it becomes dust, it will stay dust unless you add energy. So in general, anabolic reactions, taking 2 little things or multiple little things and building a big thing, that goes against the grain of the universe. The universe wants to take big things and decay them even further. So you have to add energy. This is ender. Ender and exer are 2 very common prefixes in sciences. Ender means in, exo, like to exit, out. So you're adding energy to make it happen, as opposed to this. So this is anabolic reactions, building things. Think of anabolic steroids, build muscle. As opposed to in catabolic reactions, like having A break into B and C, or one big thing breaking into smaller things, this releases energy. These are the reactions that tend to be spontaneous. They happen on their own. It goes with the flow of the universe. So you want to kind of link adding energy to building things, anabolism, releasing energy when things break apart. Think of a building if it breaks apart. It releases all that energy, right? So that's what this slide's all about. Metabolism includes both anabolism and catabolism. Think of a catastrophe, things break apart. Okay, and then we can really define trophic levels. We said earlier, do you make your own food, autotrophy or not? Really, it means source of organic compounds. So, can you make organic compounds from inorganic compounds? Self, that's autotrophy. So you can take carbon dioxide, which lacks hydrogen, so it's not organic, and water, which lacks carbon, so it's not organic. Take inorganic building blocks and build carbohydrates. You can be a photoautotroph, most are. So remember, to take little bitty things, we're going to look at photosynthesis. We're going to be taking 6 water and 6 carbon dioxide, and we're going to build one gigantic C6H12O6, one sugar molecule. We're basically taking 12 little things and building one gigantic thing. That's anabolic. It requires you to add energy. What type of energy do we add in photosynthesis to build sugar? To fix tiny little carbon dioxides into one big sugar? Energy from the sun, right? So they're photoautotrophs. There are other lithotropes or that use other inorganic materials, like in these geothermal vents, and don't ultimately rely on the sun. Ultimately, they still do rely on the sun, but they're almost completely solar independent. We, on the other hand, are organotrophs. Heterotrophs, our source of organic molecules is something other than ourselves. So it's not that we can't make sugar. We can make sugar, but we have to start with an organic molecule first. We can eat sugar and turn it into fat, one organic into another. We can take fat and turn it into blood sugar, or protein into sugar. But the molecules we start with have to already have carbon and hydrogen. As opposed to autotrophs, they can make molecules with carbon and hydrogen from molecules that don't already contain carbon and hydrogen. That's really the key difference between auto and heterotroph. Okay, super huge concept when you're dealing with the catalase test and the oxidase test. You must understand oxidation and reduction. So we're going to look at, in lab, you should be looking at the catalase test. Catalase is an antioxidant enzyme. What does that mean? What is an antioxidant? I drink red wine, not because I like the feeling it gives me, but because it contains lots of antioxidants, right? What is an antioxidant?
Do they destroy free radicals?
Okay, that's how they achieve their antioxidant, though literally means like against oxidation. It prevents oxidation. What is oxidation? So oxidation involves the loss of basically electrons and protons. Reduction, so if something loses electrons, they don't just disappear, something else has to gain the electrons. So I encourage you to memorize the acronym oil rig. So typically, sometimes it's better to focus on the hydrogen ions or the electrons, it depends. But basically, when you get oxidized, oxidation involves the loss. Think of a hydrogen atom as being lost. A hydrogen atom is a proton and an electron. That's what number 1 on the periodic table is. No neutrons. So sometimes we're interested in the electrons, sometimes we're interested in the proton. Remember, a proton all by itself, well, if you get rid of the electron, the proton, that is the same thing as saying a hydrogen ion. This always confused me when I learned about pH. Oh, when you measure pH, you're measuring the amount of hydrogen ions in the solution. Oh no, you're measuring the amount of protons in the solution. Which one is it, protons or hydrogen ions? A proton is a hydrogen ion, or a hydrogen ion is just a. If you make it ionized, you don't have the same number of positives and negatives. The only way to do that is like that, and that's just a proton, which is a hydrogen ion. So if you're losing protons and electrons, you have been oxidized. So red wine, the antioxidants like catalase and superoxide dismutase, they prevent hydrogen ions and electrons being ripped off of you. That's what it means to be oxidized. So if something loses, something else gets reduced, not in size, but in oxidative state. So it loses negative money. It's like gaining money. It's a chemistry thing. So let's look at cellular respiration and photosynthesis real quick. I'm sure I have those equations in here somewhere. Do I not have the equation written out anywhere? For realsies? Wow, I don't even have. Well, you need to recognize the equations big time. So basically, I had it up here. Well, no, I had photosynthesis up here. C6H12O6 plus oxygen. So with oxygen, you can take sugar and you can completely oxidize sugar into carbon dioxides and water. And if everything goes perfectly, which it never does, you can make as many as 38 molecules of ATP. So this really is the process. What is cellular respiration? It's how we change our stored money in our bank account into the actual money we spend every day when we go to Starbucks in the morning and stuff like that. So the machines of life run on ATP, but ATP has no shelf life. Tell me if the camera cuts out. It just did something funky. Still working? Still working? So energy stores well as fat and sugar. We must liquidate that stored molecule into ATP tokens to make the machines run. This is the main process by which we convert. Glucose is kind of the main one, but not the only one you can do in cellular respiration, with the help of oxygen to make a ton of ATP tokens to make the machines run. Right? So I encourage you to think of cellular respiration as the total oxidation of glucose. What does that mean? To completely oxidize it? What did it mean to oxidize something?
Increase the bonds to O.